What I'm going to talk about is some of the advancements that we are currently seeing in the design of bridges, and something that we hope and we anticipate to see in the coming future. And as Richard has already shown a few things, and that's why those slides I would be able to skip quickly, because the application of wind has been very well demonstrated here. But I think, as we know very well, that the technology, when we talk about technology, it has main purpose of technology is, for me, is to make things better somehow in the end for everyone. And that should be the ultimate goal. But on the process, we always find that while it makes good things better for one, it doesn't do well for others. So it's always the holistic application of the technology. So my topic was originally trends and advancement in structural design of bridges, but I'm going to modify that by removing the structural from the title, because I think we are mostly talking about holistic, so I'll go a little bit more beyond structures, but focus on structures. So let's see, we have already talked about the importance of infrastructure so much that I can skip this slide too. However, I would like to mention this, that when growing up and learning to be a structural engineer, my first thought was that I would like to design a bridge, to be a bridge designer, because I thought bridge design is an engineer's project, because you are completely in control of the whole thing. Buildings are architects' projects and we are assisting, but bridge is supposed to be our project. We can conceive, we can build, we can really make what we want out of a bridge, and we can be creative, we can be innovative, we can have aesthetics, we can have everything there. But lately I see this particular thing also slipping away from the hands of structural engineers and moving towards other disciplines. And I will talk a little bit more about that, why and how we can take it back into our hands. And that is the problem here that Richard also mentioned, life cycle. As structural engineers, we are only focusing on few parts of the life cycle. We are not thinking about the whole bridge holistically, so other people are coming in from other sides into, so to say, our domain and our terrain, and we are not covering enough. So as structural engineers, we have got to think about the whole project, because in the end, for the client, the whole project matters. Not only the structural design, for them it's one part of the big puzzle. So if we just focus on that, they don't see the value unless we attach it to the value of the whole project life cycle from the beginning to the end. And that's where I think as engineers, and because of the technology, we can move in that direction. So what are the trends that we can talk about and in the future or in the current? Obviously, advancements in materials, very important. No industry can move forward without material. We see that all around us, battery, everything is about materials. So material science is the key. Engineering, analysis, and design, obviously, that's what we excel in, and that we continue to develop that. Construction techniques are changing rapidly. We need to look for that, because adapt our designs and tools to that. Monitoring and maintenance, once again, emphasizing, that's the life cycle. Design, construction is 3 years, maintenance and monitoring is 100 years. So how can we not think about that when we do our design for that life cycle, like important part of the life cycle? Aesthetic and sustainability, we no longer can hide from these two as we did in the past. We have seen in many cities, we drive around and we see, I don't like to use this word, I'm going to make an exception, ugly bridges, ugly structures. And there has been a study on psychology that people who drive through this environment get depressed by the time they reach the office, because it's concrete jungle and it's not aesthetically pleasing. So aesthetic sustainability has to come into that. Brain-based design we talked about a lot, so I can skip that, save some time there. And embracing new emerging technology, we also saw a lot of that today, and I just focus on the bridge part of that, and collaborative design once again. So my job is quite easy because Richard set a great stage for me. About the materials, there's so much to be done and so much going on around that. This presentation is not about materials, it's about analysis, but we already know the benefits of high-performance concrete and ultra-high-performance concrete. Ultra-high-performance concrete the strength is almost as good as steel. It's amazing to see how high the strength of a concrete can get, 22,000, 25,000 psi, with the tensile strength of 7,000 psi. It's just amazing. You don't even need reinforcement in a concrete of that kind. So definitely most application will be in bridges. Then, fire reinforced polymers and lightweight concrete and so many things, and nanomaterials and stuff like that. So that's one thing, one aspect of the bridge design improvement that we must watch and closely embrace. Let me come to structural modeling, analysis and design, which most of you are actually involved in. Now, where are the enhancements going? Obviously, in the modeling, we're moving, we're getting new elements, we're getting new things, frame, shell, solids, isolators, links, hinges, we have complexities there. Analysis is that I put a lot of dotted lines because they are moving fast. Linear to static, non-linear, construction sequence, long-term effect, moving loads, and so many things. So there's one whole stream of development in that direction on the analysis and design tools and the methodologies behind that. What could be the modeling strategies for a bridge? Because it's very different from building. Because the bridge, you can actually have a clear modeling strategy. Buildings, not so many choices are there, and there's a reason behind that. But for the bridges, just start from the deck alone. You have many ways that you could model a deck. And people do that all kind of ways. Starting from a simple beam model, you put the whole deck as a beam with a cross-section, the deck as a cross-section, and then say, oh, this is my whole bridge span with one line representing that. So as an engineer, you are happy with that. Try convincing anybody else that your one line is representing a 14 or 15 meter wide bridge with 7 beams and a slab and so many things. They would not understand or agree with your model, but somehow we are happy to do that. Then we have the grid model came up when we started working on I was a student at that time, but we worked on the Donmount hallway and we started modeling that bridge using this grid model using microfield 2. It was great in that advancement at that time. Then beam shell model and all solid model, shell models and all. So many choices, each one with its own benefit, with own challenges, with own discrepancies and so on. None of them will give you the same result. And you might wonder, you should ask, which one is right? Which one should I use? Because all of them will give you a different result. So then how do you rely or justify or use those results in the end and say, oh, this is what I got and this is what I can use. Every model has, so I'm going to go a little bit more into that side, what model we should be using. For example, I am always bothered when we assume that the bearing of a deep girder, like 4 meter deep girder, is at the center of that beam model. It's not, it's 4 meter, 3 meter below the deck. How are you not seeing that as engineers in the modeling? So you can see from here that the realistic modeling needs to take care of that bridge, which is also not a real bridge. It's a model of the bridge, but at least it's a BIM model. So it's more realistic looking. It at least has all the geometry complete. But then how do you translate that into a realistic model? So we need to model the diaphragms, to the bearings, to the cap, to the everything should be geometrically complete if you are going to move forward into integrating this information with all of the other disciplines that we are working with. Over there, a line model or a pure shell model may not be sufficient. So we need to just see that we not only need, but we have the capability to remain as close to the original model as possible using various modeling options that we have. And we get the results which are also realistic. And it can, for example, when the girder deforms on the supports, the bottom of the girder moves differently. So if you don't have the bearings at that location, you can't get the bearing forces correctly if you put the bearings at the center of the beam, assuming it's a simply supported beam with 2 bearings. So you won't get the bearing displacements correct. So you can see here in modeling strategy, you could use a combination of just a frame or a shell or a full shell or even a solid model, and or just a 2D frame, that's fine too, if you're happy with that. I mean, it can be done. Tough experience, understanding, the first model is as good also, can be. But now that we have the tools, we may need to go more, and then it will be best. It's amazing to me, mechanical engineers have a device like this or smaller, and they will model it using solid elements, always, right? But we have a huge concrete block which looks very, very big and solid, and we tend to model it by a thin shell or a frame element, because somehow we don't see the dimensions correctly. So we have the opportunities to model them as realistically as possible and get the results. But yesterday they were talking that as soon as we get stresses in a model, engineers are lost. How do I calculate reinforcement from all the stresses? It's a very nice plot, but where is the reinforcement? How do I get the top bending moment, shear force and torsion? That's what they want in the end. And this doesn't give that. We need more understanding, more post-processing to be able to go to that level. And that's where now the software needs to help us with that. CSR Bridge, of course, I can't help without talking about that. CSR Bridge is one of the software that does a lot of those stuff if we are willing to put the effort and the time to do that. So this program has parametric modeling. This is one of those slides I'm going to leave you with, and then you can see this poster outside. It has a lot of modeling and analysis capabilities, a lot actually. In fact, many of them did not even fit on this slide, and that much power is available. And that's, I think, the main strength of CSS software beyond others, because the analysis capability is really deep, and then you can just keep on going and never finish. You can start with finding one thing and keep clicking all the in-depth, and you can have 11 forms open, and you still haven't to put all the information there. In my class, I normally teach material. You define your material. Okay, this is 3 values, modulus plus TE, and then from there you can go on to define the nonlinear properties of each of the material and the temperature dependent and the age dependent and so on and so forth. It never ends. And you can do all of that. Especially I want to mention this very, very powerful tool that engineers have. And if they just understand this, a lot of the problems, complex problems in bridge analysis could be solved by using the powerful nonlinear elements. Because in the modeling, we have 2 things. Things that we see and things that we don't see. So it's a physical modeling and it's a behavior modeling. For the behavior modeling, you need something that also is a behavioral concept, and nonlinear link is that. It can help you to connect or disconnect things as you want them. So it's really powerful. And if we want to really do advanced modeling, this is something that we need to learn. So just a few quick animations of what we could do for the moving load, because that's another biggest differentiator between buildings and bridges is the effect of the moving loads and the fact that they're moving all the time. So the load combinations and cases that you need to analyze are thousands if not millions. Second is the effect of the time-dependent forces. So when you construct something and you leave it there after a while because of the creep and shrinkage and relaxation and all of that stuff, things will change, especially things in bridges. And over time, what you saw in the beginning, after 5 years, it could be opposite of what you designed. So where do you stop your design without incorporating the time-dependent effects? And once again, using straight construction analysis, time-dependent materials, and so on, you could model that. This is for another example where you can see it's a benzene balance cantilever, and you will see that after that, after some time, over the time, the bending moment diagrams is changing, it's going the other way. So with time, things can completely reverse, and if we don't do that properly, in a bridge especially, we will be missing out quite a lot. And then there's something beyond structural engineering, which is the ACM. And ACM is advanced computational modeling, which combines structural engineering modeling, but also many other modeling techniques, and using CFD and all of the physical modeling that is not available in traditional structural engineering software will also be needed for example, fluid flow around the piers is one example, and so many other things. So we could do a complete, because of the main model, you could run the same model in physical behavior models and also run it for the structures and combine the effects together. Bridge, so many things could be done with that. Let me say a few words about the box girder bridges, both the opportunities and challenges. Now, box girder are becoming more prevalent than in the past. I remember one project in Sri Lanka. We had a huge debate, several months, this project that we were going to do, whether it should be traditional I-box, I-beam and all, or should be the box girder. Because this would be the first box girder, continuous box girder bridge over there. So there was a lot of debate, who will do it, who will design it, where the contractor will come, where the equipment will come. So there's a whole story behind that. But box girders are really good, and they have offered a lot of advantages in terms of the efficiency, in terms of the ease of following the complex geometries that we have in the urban areas. They just have huge advantages over traditional beams, reduce the number of expansion joints, smooth ride, incorporation of the slopes and the super elevation and all of that. But at the same time, they come with a lot of challenges because they are complex structures. And modeling them properly, your geometry is difficult. Sometimes they are segmental. So modeling their segmental construction over time is complex, it's difficult. So there is a huge challenge in analysis, in modeling analysis, and also the construction, and making sure that everything is match cast and it connects together, and the stressing sequences. So many complexities are there, both in the entire process, and people have to be really good at doing this job for this to work in the end. But let me come to another important structural component which deserves a special mention, and that is the abutments. Because abutments are the places where the soil or the road ends, bridge starts. And that is where you have two systems coming together. And this is very complex because unlike building foundation, which is below, this is on the ends of the bridge, which means it is preventing movement. And not only preventing movement, it's also imparting forces. So this is a complex in many ways. So these are the three most common types of abutment. The closed abutment, closed wall abutment, which will retain the soil on one side, bridge on the other side. So when you put the bridge over there, the abutment could be pushing the bridge, depending on the height, because of the active soil pressure. The bridge could be pushing the soil because of the movement from the vehicle braking, or with the temperature effects, or due to these earthquake movements. So we don't know what is happening at what. What are the bearings doing? What is this trailing rod doing? How much the bridge can move before it hits the end wall and pulls that? We have seen bridges falling off the abutments during earthquakes without restraining block. But then what about the restraining block? Because it will allow a little movement and then it will start to head. I remember in my bridge class several years ago, I gave an example problem to all of the class. Give me a force deformation curve of a bridge girder to the abutment from small to large displacement, and I said you can use internet, you can use open book, you can use whatever you like. And only one student got it right in the end, because it's a very conceptually difficult thing, because the whole movement is very complex. When does the abutment become active? Where is the soil stiffness, and so on and so forth. So it's a really complex thing to do, because if you look at the abutments on the two sides, I remove the slab here, and the right-hand side is the integral abutment, which is becoming very popular these days. That means no bearing between the bridge and the abutment. So the abutment is connected to the bearings, put on a very flexible set of piles, so that it just simply allows the bridge to move, hence removing many of the complexity of a traditional abutment where we talked about that. So in this case, it just becomes kind of a spring support for the bridge, because we're simply allowing the bridge to move as it wills and put it on very flexible piles, which are not really restrained by the soil also. So that's a good way to solve some of the problems. But as you can see, the approach that. First of all, if the bridge is doing nothing, the abutments are under soil pressure anyway. If the bridge is expanding in temperature, contracting in temperature, it's trying to move, abutment is trying to stop that. When the vehicle comes close to the bridge, the approach slab, the vertical load from the vehicle will put a surcharge on the side of the abutment, putting more pressure, changing the movement. And when there's an earthquake, so this is a model of an earthquake modeling on two bridges. In one, the abutment is simply supported like pins or rollers. The second one, it is flexible, real, trying to model more reality using the spring concept. And you can see how the movement will be different. The bridge, the left side and right side, you can see how much difference in the behavior can be just because we model the abutment differently. So that's how important the modeling of the abutment can be, because we can be between those two extremes. So we now have the ability to create more realistic models. The problem is getting the properties for this kind of abutment is still very hard. Soil layers and all of that is not easy. So we still need to learn more about interaction between soil and structure and all of the geotechnical properties that we need. Let me come to another interesting development. which is the generative design, parametric and generative design. We've heard a lot about parametric design, but I'm just going to combine it with the generative design. So generative design, as always, the architects were ahead of us. They adopted BIM before us. They do all the technology before us. We are always late to follow. So in parametric generative design, we can optimize, we can do a lot of things. Let me skip that. These are the first few examples of parametric design applied to real projects. The top one is by Zaha Hadid, the famous architect from, late architect from the one who did most of the buildings in the Baishis in Baku, in Azerbaijan. And the whole building was done parametrically, structurally, architecturally, aesthetically, integrated into a generative design concept. And she actually is a pioneer in doing that in architecture. So architects have been doing that now for a while, 10 years or more. Mechanical engineers aren't far behind. So they're trying to optimize. So left-hand side is a traditional handle, door handle. The right-hand side is a door handle generated by generative design. And same is the case with all the other products. This is a hinge from one of the axles from a car. So what they're doing, basically, the end is optimizing, trying to remove all the material not needed through repeated cycles. You create a solid, analyze it, wherever there's low stress, remove it, analysis, remove stress, remove material, analysis, remove material, continue to the generative design until only what is left is what is needed and everything else is gone. And that's how optimization, together with other technologies, is helping most of the other disciplines. How about structural engineering? That's the famous bridge, iconic, everybody knows that. Somebody thought, why don't I apply, go back and prove these guys wrong, that they got it wrong. Let me use generative design on this bridge and put a big box of steel and let the generative design tell me how this bridge should look like. And this is what they come up with. But that's the reality. That is the generative design of that bridge, which actually will work. We could make it like that in steel. So did other people, but it's a real project. People did a lot of research on coming back to this one, sophisticated analysis and all. But the concept is, it can be applied. You take a block of material and you go through cycles and keep removing things which are not needed. But the problem with this approach is it's uncontrolled. You end up with things that can't be made, which are not realistic, which are not practical, which are funny to some extent. So we can combine this generative design with parametric generative design, where parameters control how the generative design will proceed and which parameters cannot be changed, how much they can be changed, what are the values that they can do. And there comes this generative design with 3D printing. So they do this one and they come, this is a company there, startup, they're making bridges by using generative design and also 3D printing them because the form can be very complex for the traditional construction. So they say, okay, why don't we just, so the company is doing very well, doing pedestrian bridges in Europe. And they come up with these beautiful places and they just go and make it with 3D printing robotics. Let's come back to our bridges. And let's just talk about one element of a bridge pier. Because this is very obvious, very visible, one of the elements, and it could be very high. Alternate shapes. Piers are fascinating to me because so much opportunity for creativity in bridge piers. So these are the parameters that could define a bridge pier. Let's see what generative design could do, parametric generative design could do for this one. So parametric generative design can actually take those parameters, vary their height and dimensions in all ways and try to find where you have the real solution that you're looking for. Depending upon what you're looking for, you can define the parameters and generative design can stop there, but within those parameters and only changing the parameters that you want. And that is, you can see here that you can run thousands of iterations very quickly and come up with the final design which you couldn't conceive by yourself. And the reinforcement cage inside could also parametrically vary. So you do the same thing. When you change the parameters of the pier, the reinforcement cage follows because it's also parametrically defined. So then you can also get a cage which will be also realistic. And you can also calculate the quantities and the stresses and everything, and capacities for each cycle of generative design and check whether we are satisfying that or not. Or you could just do a generative design only optimization, the bar size and number, and then check with the capacity and all at the same time. So there is a lot of advantages in using the generative design concepts in this one. So bar size, spacing, number, all could be done. And in the end, you can end up with this whole complete cycle of the fully parametric generative, integrated design and all the terms that you have, because you start with parameters, you create a model, you create a finite element mesh, you automatically completely compatible with that, you do the stress analysis, from the stress analysis determine the actions, section cards, whatever, get the forces, depending on shear force that you will love to use, do the combo, design combos, check the PM diagram, see if it is all okay or not okay, do the rebar cage, verify that, move on to the quantities, move on to the rebar schedule, and when you're done. So you can go on and you just go back home, sleep, next day you come back, you should have your pier done. So that's the whole idea behind fully parametric generative design once we plug it into the full system. So there are many considerations that we can handle. By parametric design, we could handle situations in modeling that otherwise would be missed or that didn't matter. Cross slope in the deck, for example, the relative level of bearing changes, the abutments, the capping beams and so on, we could now handle that and keep that in the analysis model. Because if you're doing it by hand, you don't really care about bearings being 15 millimeter above the other, they are flat to you. But for a beam, that 15 millimeter or 20 millimeter matters. It's going to be constructed, it's going to be matching with the rest of the dimension, you can't ignore it. So we could put that into the system. Similarly, the proper modeling of the bearings and the girders and the ends and the cutoffs and the relative differentiation and all of that stuff could now be part of the model rather than lumping them up into a pin or a roller or something like that, right? So we could have more realistic modeling of the whole system because we keep the parametric 3D stuff intact throughout the process. And you can see that from here, the finite element mesh matches with that and everything connects to that and we maintain that. When we come back, we will not be losing any information and we will know which element belongs to which part of the pier and so on. If we want to puncture a hole in this wall, we know which element will be affected. And so we can do a complete modeling of the bridge, get all the board shapes and whatever you need from that, and you can handle all kinds of stuff. They were there with various complexities in the process. There are also advancements in construction that we need to be aware of, and we make sure that those advancements are now part of the design development. As I showed you, 3D printing, generative design, they all have to be the construction technology integrated into the whole process. Monitoring and maintenance, we cannot miss that, and in my opinion, the software should anticipate already that this bridge is going to be instrumented with IoT. How am I going to get the IoT sensor data back into me and update the model and calibrate the model and get me for the next 100 years? So rather than sell the software to the designer, give it to the owner so that they can monitor and also look at the bridge for the 100 years, not just during the design process, because the monitoring is integrated into the analysis process. We can't ignore aesthetics and sustainability, as we have been hearing since yesterday about that in our profession, or any profession for that matter now. That's why I mentioned to you, architects are coming in, sustainability consultants are coming in, all kinds of consultants are coming in, because as engineers, we are missing those integral parts in our basic design. So somebody is coming in to fix the issues that we didn't consider. So we must now incorporate sustainability as aesthetics, try to be aware of them and think about them right from the beginning. This is, by the way, this image is generated by Delhi 2, those of you who don't know, the AI image, text-to-image generator. So I basically typed a text because I wanted a picture that shows bridge and sustainability together, and I couldn't find something. So it's bridge and sustainability together, and you get an image. Right? So you can see generative text-to-image is also now becoming quite advanced. This is an interesting concept. They put the actually wind turbines inside the bridge structure, because normally bridges are on areas where the wind flow would be very high because they are between valleys. So you could integrate, somebody's idea to put these turbines there. What it will do to the bridge lateral stability is another question. Collaborative work, I don't need to say much because we heard a lot about that. So we have lots of tools to work collaboratively. BIM is a very good platform. Bring, if you use Bridge, and then use all of the other technologies, cloud computing, cloud storage, all of that stuff that we already heard about. Once again, back to life cycle, try to keep everybody together. all the state construction stages and all the people involved together in the collaborative work. Cloud-based collaborative work, now a reality, we have seen that in practice, and I'm so glad Richard's presentation before me, because then we have already seen that in action, so we know it's possible. It's not theory anymore, it's actually being done. So let me come back to a couple of concluding remarks. First of all, future trends and developments will integrate technologies, life cycle phases, sustainability, stakeholder and public interest all into that. We can't escape that anymore. And don't forget, AI will play an important role. We have already seen that. I'm just curious, how many people have not used ChatGPT? So everybody uses that. So you know how scary it is getting. So let me leave you with this thought. Very soon you might have a chatbot which will let you do this. Can you please design and detail a 150-meter long, 4-lane straight overpass bridge with a height of 7 meters using TI or T girders for highway loads using ASHTO standards? Done. You get the output. It will be pretty good. And I'm telling you, this is not too far. Thank you very much.